So there's two big types of friction. Okay, the first of which is called kinetic friction. What does kina mean? What's that root mean, or that prefix? Movement, good. Motion. Right? Our kinematics equations have to deal with objects that are in motion. So kinetic friction is friction that is acting upon an object that's in motion. Okay, so kinetic friction always opposes the velocity of an object. Okay, it acts in opposition to our object. So if my object is traveling to the right, my friction is going what direction? Left, right? That's it. Okay? And kinetic friction is specifically friction of an object that's in motion. So the magnitude of kinetic friction depends on the nature of the two sliding surfaces. So the two surfaces that are interacting, if I have an ice cube on ice, right, do we think we have very much kinetic friction? No. Now if I have sandpaper on wood, do we think we have very much kinetic friction? Yes. Yes. So kinetic friction and friction in general depends on the relationship between these two surfaces. Okay? And we're going to look at a couple tables that have specific values that can help us determine the friction depending on what the surfaces are. Okay? Friction has been found to be proportional to the normal force. Okay, so here's our equation for kinetic friction. Friction is equal to the coefficient of friction, which is what this Greek letter is right here, times the normal force. Okay? So that coefficient is just kind of a U with a little tail on the front. Okay. And they put this subscript K just showing us that it's the coefficient of kinetic friction. I don't need you to include that subscript all the time. We're going to deal with kinetic friction much more than we deal with the other type, but that's what that K is for. Right? It's telling us that it's the coefficient for kinetic friction. Okay, so to find the frictional force, we take the coefficient times the normal force. So what does that mean in terms of our friction when the normal force increases? What would happen to friction? Increases. If normal force increases, our frictional force increases. So I want to demonstrate this with you. Rest your hand on your table, just lightly. Okay? Is our normal force greater than, less than, or as it should be right now? If it's just resting lightly. As it should be, right? So you can slide your hand. Okay, do you feel too much friction? Right, it's not too bad. Now I want you to push your hand down. What would that do to the normal force? Increase it. Okay? Much more difficult to move your hand, right? If you push down, that's increasing the normal force, which increases that frictional force. Okay? Do you understand why that would be the case? Why would an increase in normal force increase our frictional force? Right? As you push down, what's happening?
There's more pressure.
Yeah, more pressure, maybe. The surfaces are interacting much closer, right? They're interacting a lot more. So if we have two surfaces like carpet, right, those two are going to slow each other down a lot the more they interact. But if you just slide something right on the top, right, that's not an increase in the normal force, so our friction is pretty much as it should be. But that increase of the normal force gives you an increase of a frictional force. Okay. The second type of frictional force is called static friction. What's it mean to be static?
Staying in place.
Not moving. Good. Staying in place. So static friction is friction of an object when it's at rest. And you can kind of think of it as the friction holding an object in place if you want to. Things just don't start randomly sliding for a number of reasons. Friction being one of those reasons. Right? If I had no friction on my desk, wouldn't all of these things just slide off because it's at an incline?
Yes.
Yeah, right? It has to do, we're going to talk about inclines next class, but it has to do with the proportion of the gravitational force, how much friction is acting, all these types of things go into why isn't this object rolling off the table, right? But friction is one of those things. So static frictional forces have to deal with the object when it's at rest. So in order for something to get started, you have to overcome that static friction. Okay, so if I want to push something from a start, right, from a rest to in motion, I have to apply enough force to overcome that frictional force. Okay, so to put an object in motion, you got to overcome static friction. And then as soon as it's in motion, what type of friction is acting? Kinetic. Good. So static only acts for a very short period of time, which is why we don't deal with it a whole lot. We deal more with kinetic friction in most of our problems. But we do look at it every once in a while. Okay? Your book labels this frictional force as F max. I will very rarely ever do that. So if you want to just rewrite that as force of friction, right, that's fine. Static friction times the normal force. You solve for it the same way. But why would it be that they say it's the maximal friction force? That's right. It's not moving. So our static friction should always be greater than our kinetic friction. Always, always, always. Okay? So the maximum amount of friction is what's keeping it in place, right? We wouldn't have enough friction to move it backwards, right? Friction doesn't randomly put things into motion in the opposite direction. So the maximum amount of friction would be considered at static friction. If you want to write one of those equations on your equation sheet, I don't think you need both. If I'm going to write it on my equation sheet, I would just say frictional force equals coefficient times the normal. That's what I'll give you all the time. You have to apply, is it the kinetic friction or the static friction? And the only difference that goes into that is that coefficient. Okay, and they just have different values. Those coefficients of friction will be given to you.
So you think there might be like problems if they give us both, but we only need to use one?
Rarely.
Is there friction if like our book is just sitting on a table flat, no incline?
And it depends on these two surfaces. So since this is shiny and pretty slick, that friction is not going to be a whole lot. If your book was covered in carpet, right, then we'd have more friction. So it's all about the surfaces that are interacting. Okay, so if you go to page 96 in your textbook, it's going to explain the difference between static and kinetic friction a little bit more eloquently than I can. Okay? So you've heard it, now I want you to read it a couple times before we practice. Right? If you look on page 97, it tells you that the coefficient of static friction are always larger than the coefficient of kinetic friction. What are some examples in which that is not the case, or they're maybe the same?
Synovial joints.
Okay, and what are synovial joints? Anybody in anatomy know what that is yet?
It's the tissue membrane in between the
Look at you. Okay. That would be not good for us if our kinetic friction was less than our static friction. That may be really hard for us to get things started. Right? That would stink. Okay. Teflon, do you know what Teflon is?
part of it.
Yeah, it goes on like non-stick cookware. Right? That's the coating that you'll see on like non-stick cookware. So that makes things hopefully frictionless. Those are some materials in which we see really low amounts of friction, so there's not much difference between static and kinetic. For most everyday materials, we see a pretty big jump between static and kinetic. Okay? All right. Very good. Let's try one here. Okay, overall goal is going to be find the horizontal acceleration, but there's lots of different things we have to do to get to that point. Okay, so I'll leave these questions up here. These are kind of check marks that you can go by when you're solving these types of problems. But you don't have to answer into each of these individually, right? This is just kind of the process. First thing we should have for all of our problems is a... Yeah, free body diagram. Good, good. Okay, so we have gravity. We have the normal force. We have a pulling force of 75. Right, we can call that F applied, or F pull, or whatever you want to call it. We've got some frictional force. Okay, so you can do this a couple different ways, solve for all of these things individually. I like to plug everything into one equation, right, and just go from there. So in this problem, is our object accelerating in the vertical direction? No. So what does that tell us about our normal force and our gravitational force? They're equal. Yeah, together they would equal 0. Our net force would be 0, but that means they would equal each other. Okay? So if we start solving for Fg or Fn, right, Fg equals Fn, and what do we know Fg is always equal to? What times what? Mass times gravity. So the mass is 50, gravity is 9.8, which means our normal force and our gravitational force both are equal to 490 newtons. Would we agree with that?
Yep.
Okay. We're on the same page so far? Okay, so now that's my vertical forces. I'm not super concerned with what's going on vertically here because I want to find my horizontal acceleration. But the reason I need that is because the frictional force is dependent upon that normal force. So that's why I have to have that. Okay, so in the x direction, my net force would say net force equals my applied force minus my frictional force. Would we all agree there? Okay. It says we're solving for acceleration, so that means we know our net force is not 0 in this case. Right? So I'm just going to go ahead and substitute our mass times acceleration, since we know we're solving for A. My applied force is 75. Right? And what can I substitute for my frictional force? Good. The coefficient times the normal, so I'll say 0.010 times 490. Okay? You could always solve for the frictional force on its own, right? I could say frictional force equals 0.010 times 490, right? And I get 4.9, and then I could plug in 4.9 to that part of the problem, right? You can solve them all separately, or you can solve them in one equation. That's totally up to you. Yeah?
What's the formula to find frictional force?
Coefficient times the normal. Coefficient times the normal. That needs to be on your equation sheet if you don't have it yet. Coefficient times the normal. Okay, so that gives us 75 minus 4.9. I think I did that math right. Okay, which should give us 50 times A equals what? 70.1. And then how do we get A by itself? Divide 50 over. A lot of you will try to subtract that. Divide 50 over. We should get a little over 1. 1.2, 1.3, we're 1.4. And what would our units be here? Good, because it's an acceleration. Perfect. Okay, so try this by yourself or in small groups if you'd like. But it's pretty similar to the one we just finished. It's Halloween, so I'll use black and orange. I didn't really mean to do that. She's an old lady. Yeah. She has a walker and everything. Yeah, they're doing what at Chrissy King? Okay, Colin, what'd you have?
For the acceleration?
Yep, final acceleration, what'd you have?
1.19 meters per second.
1.19 meters per second squared, I would agree. 1.2, whatever. Okay, so now we start dealing with friction when we have two-dimensional forces. So those were easy ones. Now we're dealing with things at an angle, right? Which doesn't change anything. We're just having to break things down into x and y. Okay, so it says a 30-kilogram box is sitting on a wooden floor. A girl pulls upward with 100 newtons at an angle of 40 degrees. The box begins to slide despite that the coefficient of kinetic friction is 0.3. So in this problem, we're pulling up on something, right? We're dragging it with a rope or however we're pulling on this box. Where does our friction look like this? Or does it look like this? Yeah. Why does it go completely horizontal? Yeah, it's opposing the motion between the box and the floor, right? It's not opposing her pulling on something. It's opposing the box and the floor. So our frictional force is still purely horizontal. Our frictional force should always be perpendicular with parallel to our surface, right? And here we're sitting on the ground. So first thing we need to do is break this into F applied Y and F applied X. And again, here I think we're trying to solve for our horizontal acceleration. I didn't pull out all the questions here. Let me do that. I think we're solving for acceleration. Let me click ahead a little bit here. Yeah, horizontal acceleration. Okay. I'm going to get rid of that so we have... Okay, make sure your calculator needs to be in degrees, not radians. Will we need to solve for both F applied X and F applied Y?
No.
Why not? Okay. Is our normal force and our gravitational force purely equal to each other? No. Because if it's not moving in the vertical direction, that means this plus this have to equal gravity. So you do need to solve for both of those things. Okay, so let's talk about it again. Since it's not moving in the vertical direction, all of our upward forces added together have to equal our downward forces. So you have to solve for F applied X and F applied Y. Okay, you got to have both of those. So for X, I'm using cosine. And I got 76.6. And for Y, I'm using sine. And I got 64.3. Okay, would we agree with that so far? Okay, so the first thing I want to do is I want to look at the y's first because I need to find the normal force. And in this problem, it's not equal to our gravitational force because there's another upward force acting. Right? There's another vertical force. It's not just those equal. Okay, so I'm going to look in the y direction first. And I'm going to say the net force in the y direction is equal to normal plus F applied Y minus gravity. Okay, would we agree that those are all of our vertical forces? Okay, if you want to put little y direction there, you can just to remind yourself that this is the y. You don't have to do that. Okay, what is the net force in the y direction? It's 0, right? Because it's not moving vertically. Okay, we're solving for the normal force. We know F applied Y is 64.3. And Fg we know is equal to mass times gravity. Okay, do we know where all of these numbers are coming from? Can we see that? So now to get the normal force by itself, we should add over that 229.7. And that means that our normal force is equal to 229.7 newtons. Okay, do we see how we got that part?
Yep.
Okay, it is less than it would be if our object was just at rest, right? If our object was at rest, our normal force would have been 294. But here we're pulling upward on that box, which means we're taking some pressure off the normal force, right? We're relieving the normal force a little bit. So now we can start looking at our x direction. Okay, so I'm going to pull that over here. We want to solve for our horizontal acceleration, so we're going to say F net equals, what's our positive horizontal force? Yeah, good. F applied x, which is 76.6, minus our frictional force, right? Okay, so I'm going to say mass times acceleration, and I'm going to go ahead and put numbers in there. 76.6. And how do we solve for frictional force?
The coefficient.
Good. Coefficient times the normal force. So that's where that 0.3 comes from, right? 0.3 is our coefficient, and 229.7 is our normal force. So that's just a substitution that happened. Okay, are we seeing that?
Yeah.
Okay, so now let's do that math. Again, it should be pretty similar to the one we just saw, but you're welcome to work with a partner if you'd like. It's not moving. So in this case, we are not in motion, right? If we're not applying enough force to overcome static friction, we can't accelerate. Okay? So when we're not in motion, or when we're not applying enough force to overcome static friction, we can't be in motion. Okay? All right, good. So if you ever get an acceleration like that, that's negative just based on friction, that means we're not moving. Okay? All right, go ahead and try this last one on your own. You're solving this time for coefficient of friction instead of acceleration. Okay, and this one's not a trick, I promise. Not that the last one was a trick necessarily.
Last time, because I didn't know what I was doing.
Did you make sure to divide by negative 882? Yeah, so divide over the negative and the... Right, because when you subtract it over the 320, that would give you negative 212 equals negative u times 882. You know what I'm saying? So if you rearranged it, it would look like negative 882 times, you know. So if you just rearranged it, it would make it easier for you to see, but yeah, that's what you need to do. Did we get it to come out at 0.240? Yeah. Okay, good.